Okay, here we are in Calculus 30, Chapter 5. We're looking at curve sketching as the title for this chapter. And as we move through this chapter, we are going to examine characteristics of curves, functions that are big and ugly, and we don't know much about them, what they look like, but we're going to be able to draw characteristics from these equations. We're going to look at the first derivative and see what that tells us. We already know about local extrema, right? About local maxes and mins. We know from Pre-Cal 30 about end behavior and intercepts and all that sort of stuff. The second derivative will tell us about concavity, whether it opens downward or opens upward over an interval. So we're going to be doing integrating all sorts of pre-calculus and calculus concepts to be able to accurately sketch the graph without actually plotting points or using technology to graph it. So we're going to put all this together and be able to sketch a graph without any technological help, kind of thing, using calculus methods. So this is a review and preview to Chapter 5, little bit here, just so we understand that this is not being taught here in this calculus course. This is stuff that you should know. For example, intercepts, okay? So you know about intercepts. These are the points on the x and y axes where the graph crosses or touches. And so if we have, something like this, xy plane, and we have a graph like this, is it frozen?
Yeah.
I'm sorry, frozen. Unfrozen. Intercepts. So if we have a graph kind of looks like this, then what we'd be able to notice is that we would have, let's say, it looks like an x-intercept here and an x-intercept here, because that barely dips below the line, and we have a y-intercept here. Okay, so you will anticipate for a function, okay, for a y-intercept for a function, that there will only be one y-intercept. And unless it is discontinuous at the vertical line x equals 0, unless it's discontinuous, you will always have one y-intercept. You won't have two, because if it doubles back over itself, it's not a function. Now, x-intercepts, depending on the degree of the function, you could have none. 1, 2, 3, 4. You could have as many, I believe it's as many as the degree of the function you could have intercepts, right? So if you have a cubic function, you could have up to 3 intercepts. And we'll find out a little bit more about that too. If you remember from, and I'll just do this little bit here too, if you remember from Pre-Cal 30, that if you have an even degree function like a parabola, you could have 0 intercepts where it doesn't touch the x-axis. You could have 1 intercept where the vertex is on the x-axis, or you could have 2 intercepts where it dips below the x-axis and that kind of thing. And if it opens downward, it would be just the same. Like it could be like this. You have 2, you have 1, and you have 0, right? So maximum of 2. Now, if it's an odd function, that is degree 3, let's say, you could have, 1 x-intercept, like that, y equals x cubed. You could have more than, you could have 2, 1 there and 1 there, or you could have 3, 1, 2, 3, right? So you can have up to 3, but with an odd function, you can't have 0 because of the end behavior. Remember the end behavior bit? So if it's odd function, it's going to span across the x-axis there. If it's an even function, the end behavior, right, is either both up quadrants 1 and 2 or quadrants 3 and 4. But if it's odd, it's always going to cross the x-axis. Okay, so find the x-intercepts, or find the intercepts of the following curves. So if we did this, what we'd want to do is remember this part, that to find the x-intercepts, you set y equal to 0 and then solve for x. Okay, so x-intercepts set the opposite equal to 0, right? So if we want to find out the x-intercepts, I need to find out what the values are when y equals 0, this blue line right here. So what are those x-intercepts? For the y-intercept, we set x equals 0 and solve. And so when x equals 0, I want to find out what are the points on x equals 0 there. What are the points here? Point. So for this one, if we want to find the x-intercept, I'll just kind of do one example here. So I'm going to let the y equals 0, right? And we'll have 4x squared equals 25. X squared equals 25 over 4. x equals. Now when you take the square root, please remember to do plus or minus. And this is going to be, that's a perfect square, so it's 5. That's a perfect square. 5 over 2. So plus or minus 5 over 2. So if this is negative 5 over 2, there's 1. And if this is positive 5 over 2, there's another one. Okay, you don't know much about well, I mean, we do know a lot about this because of Pre-Cal 30. It's a squared, so it's degree 2, so it's a parabola. The coefficient on the x squared term is negative, so it opens downward, right? And we have a y-intercept of 25. Now notice that this is symmetrical, so negative 5 over 2 and positive 5 over 2 is symmetrical, so the vertex is on the y-axis there, and it opens down. Right? So all of that. So we like, without any calculus, we know a lot about a parabola because we've studied parabolas for years already, right? All right, so the y-intercept, this one's easy too. So we simply let x equals 0 and solve for y, right? So 25 minus 4 times 0 squared, which is y equals 25. And we know as a quadratic, the constant is the y-intercept always, and that's y. Okay? So you do the same thing here. I would maybe just highlight that when you set when you set y equals 0 to solve for the x-intercepts, you have some restrictions here, okay, possibly. You don't here because x squared will always be positive, so this will never be 0. But what you do is you focus on the numerator, okay? So wherever this equals 0, that's where the whole thing equals 0. Because if you have 0 over a number, then that whole thing is 0. So you're focusing on the top there. This, it provides restrictions, possibly. So if there's a restriction here and you say, oh, that's one of the x-intercepts, but it's actually a restricted value, then it's not. It's some kind of asymptote. But when you're looking for, again, when you're looking for x-intercepts, you set y equals 0, then just focus on the numerator because that's what's important. When the numerator equals 0, that's when the whole thing equals 0. Okay, so that's a bit of a note with rationals. Factoring, so if you remember this one, like here, D, right? So if you factor this, that will give us an indication of what the x-intercepts will be. So can we do this? Oh, that one looks a little iffy. Yeah, we have to multiply to 1, but add to 1 as well. So is that possible? Any factors of 1 that add up to 1? Well, if you're not sure if you can do that by sight, factor by sight, which is what you might want to try, then remember you can always do the quadratic formula, right? Whoops, x equals negative b plus or minus root b squared minus 4ac all over 2a. And then this is the discriminant. Remember this part here? It's called the discriminant. Yeah. I'm just teaching that in, Pre-Cal 20 last week. No, Pre-Cal 20, I believe, yeah. Yep. And so if you check b squared minus 4ac, this is going to be 1 squared minus 4 times 1 times 1. That's going to be 1 minus 4 is a negative number. So that's a problem. So what does that mean then? That means that there are no x solutions to this. That means there's no x-intercepts, looks like. Okay. All right. So this is a parabola that opens upward. It has a y-intercept of positive 1. We don't know if it dips down at all, but it doesn't appear that it dips down and touches the x-axis at all.
We didn't even have to do that, because if it starts at 1 and it goes...
Well, it doesn't. I mean, this is the x-intercept. We don't know if it starts at 1.
The x-intercept?
I'm sorry, the y-intercept. But we don't know if it's like this. It could be like this, right? Like you don't really know where it dips down, right? So it does open upward. What is the vertex? Do you remember how to find the vertex from a quadratic? Wow, you guys are remembering. Great. So negative 1 over 2 times 1 is negative 1/2. So negative 1/2, let's say, is right here. And so what happens when I put negative 1/2 in there? What do I, negative 1/2? What do I get? 1/2 squared is 1/4 plus 1/2 plus 1.
Wait, it's negative 1/2. But it's squared.
This is minus. You're right. This is minus. Thank you. So this is going to be what?
3/4.
Positive 3/4. So we have negative 1/2, positive 3/4. That's your vertex. It opens upwards.
Awesome.
So it doesn't. In fact, doesn't touch. And the discriminant would tell us that. Okay, that's a lot of pre-cal stuff. That's good. But are we good with the x-intercepts there?
Yeah.
Kind of understand though what's going on over there?
Understand.
Okay, let's talk about symmetry. Now, we touched on this briefly in Pre-Cal 30. We're gonna explore this a lot more here now, so let me just take a bit of time here. An even function. Now, we've often thought that, x squared plus 5, that this degree is even, and so that would make this an even function. Now, when we talk about symmetry, okay, we have to be very clear on what an even function and odd function is. It's not good enough, really, just to look at the degree of the function. That's not the same. So even does not mean degree of the function, simply. What an even function is, as it pertains to symmetry, and this is what's important in this section, is that when you plug a negative value for x into the function, it yields the exact same value as if you were to plug in the positive value for that. So let's take y equals x squared, for example, okay? Y equals x squared. So if I plug in f of, and you know what, -1 and +1 are always good to try if you can. Use those because they're easy, right? To plug in -1. 1 squared is 1 and all this sort of stuff. So we have y equals -1 squared, y equals 1, okay? So f of -1 is 1. F of +1 is going to be y equals +1 squared, which is also 1. So this tells us that y equals x squared is in fact an even function, and it does have some symmetry. Now, the symmetry that we will talk about as this kind of goes on, I don't need to fully talk about it now because it'll come up later, but the symmetry in the even function, if you consider what quadratics looked like, an even function has symmetry about the y-axis. So you might want to write that down. If it's even, it has symmetry about the y-axis. And in our case that we just did right here, of course, this is y equals x squared, and it is symmetrical about the y-axis. That means that the axis of symmetry is right on the y-axis. Okay? So an even function has symmetry about the y-axis always. Now, let's go back to this one, like +5. So if I did y equals x squared plus 5, what you should know about this graph is that this parabola is simply moved where? How is this parabola moved? It's 5 units up, right?
Oh, my bad.
Straight up, because this is outside of the x squared part. It's not x plus 5 all squared. It's x squared and then plus 5. So this is moved up. So does it still have symmetry?
Yeah.
It still does have symmetry about the y-axis. So let's just check to see if this all holds true. So what I would do is if I have a +5 there, I would do +5, and this would be +5, which is equal to 6, right? This would be +5, which +5 equals 6. So the value is still the same, okay? Now, there are lots of functions that are not symmetrical about the x-axis. For example, if we had x plus 5 and then all squared like this, okay? Let's check this one, okay? Let's just check this one and see. Now, we know what happens to this parabola because of your work in Pre-Cal 30. Does anyone remember?
It goes.
Thank you. It's a parabola that opens upward, and instead of having a vertex at the origin, it's moved left 5 units. Okay, well, let's just see what happens here then. So if it's moved left 5 units, then we would think that there wouldn't be symmetry about the y-axis. There would be symmetry somewhere else, right? So let's just see. So f to the -1, this is going to be 4 squared, which is 16, right? -1 plus 5 is 4. This one, 1 plus 5 is 6. So this is going to be 6 squared, which is 36. Obviously, we do not have symmetry, okay? So this is not an even function with symmetry about the x-axis. So let me just clarify that over here. So we've moved this parabola way over here, right? Okay, hang on. We've moved this parabola over here. Just hang on for a second. X, -1, or sorry, to the left, my bad. Okay. Yeah, so we've got -1. -1 here has a value of 16, and +1 has a value of 36. See how it's way higher? So that does not give us a symmetry about the y-axis. These values should be the exact same if there's going to be symmetry, either there and there or there and there. So because they're not the same, we know that it's not symmetrical about the y-axis. Got it? Okay? All right, an odd function, let's talk about an odd function. Lots of times, not all the time, but if you have an odd degree function, that is sometimes odd. Not always, but sometimes. And so an odd function says this: if you replace a negative value and a positive value into the same function, then this will be overall positive value of something, and this will be overall negative. So the negative is outside there. So you have the same number but opposite sign. So y equals x cubed, let's try -1 and +1. So you have -1 all cubed, and you have +1 all cubed. So this is -1 here, and this is +1. Now it doesn't matter if this is negative and I wrote this as being positive. It doesn't matter. One is negative and one is positive. That's what we know. Okay? Because if this was -1, which it is, then this is -1, which it is. Yes.
Wouldn't the left function be -1? Because x is -1.
No, what you do is you plug into the function, into the f. Oh, disappeared. Into the f you plug a negative value. Into the f you plug a positive same value. And then you just compare the answers. So if they're the same numerical value, same magnitude, like 1 in this case, but opposite signs, then it's odd function. Okay? Yeah, so, this value is -1, this value is -1. It follows this pattern, you see? Follows the pattern. One's positive, one's negative. So I won't probably do any more, but just substitute a positive value and then the negative of the same value. So what is the symmetry of an odd function? Well, let's talk about that. An odd function has symmetry about the origin. It's not a line, it's a point. And it has symmetry about the origin. So this is going to be very important for us as we examine equations of lines, okay? What the symmetry is. It's going to help us graph this. So this is y equals x cubed right here. And if we go over 1, up 1, there's our +1. If we go -1, -1, there's our -1. And so if we did that to any values, +5, -5, +17/2, -17/2, we would get these points that are symmetrical about the origin. And what's important to note is that it is rotational symmetry about a point. If it's an origin, that's a point. Okay, so it has point symmetry, which is rotational symmetry. And hopefully you can see that with the y equals x cubed. So we have vertical line symmetry about the y-axis for even, and we have point symmetry about the origin, which is rotational symmetry. And if you don't remember what rotational symmetry is, hopefully you do, but if I were to take this graph and grab it by the horns there and then crank it around and spin it like I'm driving a bus, then what would happen is this would, it would spin around like this. Well, it would map onto itself here, actually. And then I could keep going, and it would map there, and then it would come back to its own position. So it has symmetry about the origin. If you rotate it about the origin, it will map onto itself at least once. That's what rotational symmetry is. And it might be more than once, it might be just once. Okay? Any questions about that? Even odd function or the symmetry that they tell us about. Yeah?
So for an odd function, if it has any transformations up or to the side, it's not like an odd function then?
Right. Well, okay. So right. I mean, if this was +2, right, then it wouldn't be symmetrical about the origin. It would be like this now. And so if you rotate it about the origin, which is tough to draw, but it would be like this, right? It would be like that.
Right.
You know what I mean? And then something like this. So it wouldn't map onto itself. It would map onto itself after one complete term, but everything does. So maybe I need to back up there. It will map onto itself once before you get at least once before you get a full-time round, because everything maps onto itself after one complete rotation about the origin, I guess. So yeah, I don't know what I spoke there a few minutes ago, but if it maps onto itself, like anything will map onto itself, and it's still tough to draw, but if you had some crazy function like this, right? Then if you spin it all the way around, it will map onto itself after one. So it has to map onto itself within, before one complete rotation. Yeah. Yeah. Okay. Okay, I think I just explained this a little bit here. Rotational symmetry about the origin occurs when you rotate the graph around the origin and the graph maps onto itself before one complete rotation. So there's that explanation. Also, just another note that you might want to remember is that for every point x, y on an odd function, there is a negative x, negative y point also on that function. So if you find one single point on an odd function that has rotational symmetry about the origin, let me just think about this for a second. Yeah, if there's a rotational symmetry about the point, if it's an odd function, yeah, you can always count on this too. So whatever point you end up, if you do find a point, local max or whatever, there's also a mirror local min. Okay, determine whether each function is even or odd in either. So let's just do a couple examples here. This one's pretty easy, right? I kind of did one with x squared. So it's x to the 6, so this is +1 and +1. So this is even. This one here, -1. So let's do -1 cubed plus 1 over -1. That's going to be -1 minus 1. That's -2. Over here, if I plug in just g of 1, let me just check that first. So I'll do this in another color. G of 1, so that's 1 cubed plus 1 over 1. That's 1 plus 1 is +2. So what we notice is that this is a negative a and a positive a. The numbers are the same, the signs are opposite, so this is odd. Okay, x cubed. I will map this. Let me graph this for you real quick. So here's that function, x cubed plus 1 over x. We obviously have a bit of a problem at 0, right? If x was 0, we have a bit of a problem there, so there's our vertical asymptote. But if you were to spin this around the origin there, it would map onto itself halfway around, right? This would spin down to here, and this would spin up to there. So this does have rotational symmetry. Yeah, it has to be in less than 1 full rotation. So if it maps onto itself at least once within one full rotation, then yeah, then you're good. Then it's odd. Okay. All right, this one here, let's do one more. This C here. So -1 cubed plus 2 times -1 minus 1. That's going to be -1 minus 2 minus 1. That's -4. Over here, this is 1 cubed plus 2 times 1 minus 1. That's 1 plus 2 minus 1 is 2. So if you come across this, it's like, wait, it's neither even nor odd. Yes, it's neither even nor odd. That is fine. That means that there's no symmetry about the origin or about the y-axis. So it's just some random function that's been, moved around like whatever. This is something like, maybe something like this, right? So it doesn't map onto itself if you spin it around within 1 full turn. That could be something like that, which is neither. And most functions are. But in the case where you do have an even or an odd function, it just makes curve sketching, which is what Chapter 5 is all about, it makes it a bit easier, right? Because if you know you have a point here and it's an odd function, there's one over here, right? And if this is a local max, well, this is a local min, because all the other points would have to mirror it, and so on. So, yeah. Okay, if this is an x-intercept, this is an x-intercept, right? Okay. Look at that. See that? So that would be an odd function of some sort. But if it's neither, then it could be, something like that. Just not symmetrical. Okay, so those are the 2 main things I want to talk to you about in the review and preview: intercepts and symmetry. That's going to be importante. Any questions about that?